Hello, hello. In today's video, we're going to be looking at single bonds and multiple bonds and how they arise through orbital overlap. So we'll look at the idea of sigma and pi bonds, and we'll also look at the idea of delocalization. So we're going to be looking at our single and multiple bonds through orbital overlap. Okay, so when we have direct overlap of orbitals between two atoms, we form what's called a sigma bond. So when direct orbital overlap occurs, a sigma bond is formed. Okay, and these sigma bonds look something like this. So if we have hydrogen overlapping with carbon, that is a direct overlap, an end-to-end overlap. And when that occurs, we call this a sigma bond. However, that's not the only type of orbital overlap we can have. We can have indirect overlap. So when indirect orbital overlap occurs, this is when we produce a pi bond. So a pi bond is formed. Okay, so I mean something like this, where we have two unhybridized p orbitals. And they are parallel to each other. This will form a pi bond. So what happens is we share electron density above and below our internuclear axis. With a sigma bond, we are along the internuclear axis. Okay, so those are the two types of bonds we can form through orbital overlap, either direct, getting our sigma bond, indirect, getting our pi bonds. Whenever we think about a single bond, so a single bond is a sigma bond. So this is the direct overlap of orbitals will produce a sigma bond or one sigma bond. Now, we can only directly overlap orbitals along an internuclear axis once. So if we think about a double bond or a triple bond, we have to have a different type of orbital overlap. We can't have sigma bond we can't have multiple sigma bonds. So in a double bond, we have one sigma bond. That's what's kind of holding everything together. And then additional overlap leads us to even stronger bonds, which is why a double bond is stronger, where we have one pi bond. Triple bond, even stronger, is going to have even more orbital overlap. So we have one sigma and two pi bonds. Okay, so the pi bonds themselves, as I said, they are the overlap of p orbitals. They have to be parallel to each other. So we can have py, py, so py from one atom, py from another, or we can have px px. Okay, remember we have x, y, and z as options. So let's look at see how we would draw these. So let's look at draw sigma and pi bonds. So a common example of a sigma bond and a pi bond together in a molecule is C2H4. C2H4, if we were to draw out the Lewis structure, looks like this. Remember, each of our single bonds are a sigma bond, and each of our pi bonds, each of our single bonds are sigma bonds. Each of our double bonds have a sigma bond, and a pi bond. So we have our sigma bonds in blue, and then our pi bond in red. When we actually draw this out as orbital overlap, we would have direct overlap between each of our atoms. We have to have that direct overlap to have an actual bond. Like so. And then we have one double bond. So we draw it. I usually draw them as lines. So here are two lobes of our p orbital, and then the two lobes of our other p orbital. So this is the lobe of the p orbitals, and then this is going to be that indirect overlap. So this would be our pi bond. Pi bond is above and below the internuclear axis. This is a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond along the internuclear axes. And that's how we draw. Then we could look at something like C2H2, something that has a triple bond. And again, we still have this direct overlap. Like so. We have one of our pi bonds, and then 90 degrees away from that is our other one. Like so. Now, thinking about this, looking at our number of electron domains, we know that this carbon right here is sp2 hybridized. And then we know this is unhybridized, so we're talking about s orbital. And then here we are sp hybridized. So when we're thinking about what orbital overlap or what orbitals are overlapping to produce these, we would say that the carbon-carbon bond right here is the overlap between sp2, sp2, and pp. And then here we've got that carbon-hydrogen bond is sp2 overlapping with an s. Down here, our carbon-carbon is sp overlapping with sp, and then it's got two pp overlaps. And then our carbon-hydrogen is sp overlapping with s. Okay. So hopefully you notice that our sigma bond, all bonds, all covalent bonds, contain one sigma bond. And the bond is along the internuclear axis. So that means the electron density here is along the internuclear axis. And then with our pi bonds, a double bond contains one pi bond. A triple bond contains two pi bonds. The pi bond itself is above and below the internuclear axis. And because of this, that's where the electron density is. There is no electron density along the internuclear axis in a pi bond. If you have one pi bond, you can call it px overlapping px. If you have two pi bonds, you can say one's px px, one's py py. But they will be the same orientation in space in order to get them to align and produce that indirect overlap. If they are not directly parallel with each other, they will not produce that pi bond. Okay, so shifting a little bit, we're going to look at resonance structures. And we're going to look at the delocalization with this. Okay, so if we think about something like benzene. When we write benzene, we draw it like this. Where we have alternating single and double bonds, but we actually know if we draw out our resonance hybrid, that it'll look like this. Where each of these bonds are 1.5 bonds instead of alternating single and double. So in order for this to occur, we have to have overlap between our pi orbitals, or pi bonds. We have to have our p orbitals overlapping each other. So if we look at this, we can look at our sigma system, our system of sigma bonds. And we get something that looks like this. An artist I am not. So we have all of that direct overlap, which forms our actual structure, and then reinforcing our structure are those p orbitals. And the p orbitals in this case, I'm just going to draw this, are all going to be parallel with each other, which allows us to have that resonance, right? So we can have it here, 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 right? Or here, here, and here. But overall, what we actually get, again, because we have that hybrid, is just overall. So we are sharing that electron density all around, and this is our resonance. And we will see this with any type of structure that shows resonance. So if we were to look at something like NO3 minus, here we have these resonance structures. Sorry, just being lazy. And there we go. Our three resonance structures for NO3 minus. And then our hybrid would look something like this. Where we've got those floating electrons or delocalized electrons moving from place to place. And in terms of drawing it as a structure, we would have if we're looking at just the pi's, we'd have a pi bond here, pi bond here, pi bond here, or pi p orbital rather, and we'd be sharing the electron density throughout the entire thing, and all of these, oops, all of these are going to be parallel to each other. Okay, so just some concluding notes about our sorry, some concluding notes about our sigma and pi bonding. When we have bonded atoms that share one or more pairs of electrons, we have a sigma or pi bond. So our bottom atoms would share one or more pairs of electrons. We produce, or we have, sigma and pi bonds. Sigma and pi bonds. So 1 pair, 1 sigma. 2 pairs, 1 sigma, 1 pi. 3 pairs, 1 sigma, 2 pi. Okay? Our sigma bonds themselves are always localized. Sigma bonds, always localized. The electrons do not move. If you move the sigma bonds, you no longer have atoms that are bonded to each other. Okay, so they're not going to share or go to any other atom. They are going to stay put between their 2 atoms. However, if we have multiple bonds with our pi electrons, these can delocalize if there are adjacent p orbitals that are parallel to them. So we see here, these are all parallel, so they can move between, the electrons can move between all of these atoms, but they would be delocalized. So that would give us delocalized electrons. Okay, so that is about it for this. We just want a example. So the whole thing, going through hybridization and looking at the pi bonds and such. So let's look at C2H2. So if we have C2H2, we have carbon with the electron configuration 1s, 2s, 2p. Like so. And then each of our hydrogens are 1s. Okay. So through hybridization, we are going to take 2 of our orbitals and combine them and hybridize them. So we're going to combine these 2, but one of these electrons is going to go here. The reason it does this is because we need single bonds. So through hybridization, we will produce 2 orbitals that are sp hybridized, and we'll still have those 2p orbitals right there. And all of them will have unpaired electrons. We'll still, of course, have that 1s in there. It's core, so it's not going to do anything. And our hydrogen doesn't do anything. It just stays as 1s. It already has that 1 electron that's in an orbital. It's good to go. So we will have a carbon that is surrounded by 2 sp hybridized orbitals, and then it's going to have 2 unhybridized p orbitals that are going to be 90 degrees away from each other. We have 2 carbons that are the same hybridization, so we're going to have the same thing occur here. So carbon, there's that overlap right there, and then our unhybridized p's there, forming our pi bonds. Then hydrogen unites each side, like so. And there we go. Now, when we look at this is a sigma bond, sigma bond, sigma bond, pi bond, pi bond, sigma bond. Okay, that's everything for this video. I will talk to you guys later.